So, hello everyone. Welcome to the discussion session. So, this will be the last discussion session of this course. Um, so, this course is offered by NPTL, and it is run and it is taken by Professor I.K. Rana, Basic Analysis course, and I am one of the TA taking these discussion sessions. If you are watching it on YouTube, uh, if if you find any difficulty understanding any argument or have any question, you can comment it down in the video below the video. Okay, so let's wait for a couple of minutes and then we will start. Okay, so let me formally introduce myself. I am Prerak from Bhopal, and I take this live discussion with you guys. Recording of these sessions will be available on my YouTube channel, which is named as Maths with Prerak. Okay, so let's discuss some questions. So in today's discussion, I have taken questions from the assignment, from the last assignment of week 12, and I will be discussing questions from that assignment only. So all of you might have already seen the questions before. So yeah, so I will be discussing the solutions of these questions. So the first question is, we need to state whether it is true or false. We define a function for each n natural number, uh, as the function is fn from close interval 0 comma 1 to r, defined as fnx to be nx plus sine nx square divided by n for all x in the close interval 0 comma 1. Now then the sequence fn is converges to the identity function on the closed interval 0 comma 1 uniformly. That's what we need to show. Okay, so uh, so here are a few things. So we have given a sequence of functions, and we need to show that it converges to the identity functions uniformly. Okay, so let us first. So this. So let us first try to prove this question. Okay. So we have given f n x to be nx plus sine of nx square divided by x. Okay. For x in 0 comma 1 interval, and fx is x. Now claim is fnx. Claim is that fn converges to f uniformly. Sorry, it is divided by n, not x. Okay, so let us quickly recall what do we mean by uh, a sequence of functions converging to a function uniformly. It simply means that for an epsilon greater than 0, for an epsilon greater than 0, there exists an n in natural number. Let's take that n to be capital N, uh, such that fn of x minus fx, this difference, absolute value of this difference is smaller than epsilon for all n greater than or equal to capital N, and for all x belonging to this closed interval 0 comma 1. Okay, so this is the then we say fn converges to f uniformly. Okay, so what do we need to prove? We start with some epsilon. Okay, we will start with some epsilon. We need to find out a natural number such that this inequality is being satisfied. Okay, and the point here is that this natural number n only depends on epsilon. It doesn't depend on the points. Uh, it doesn't depend on the point you are choosing. Okay, so it only depends on the epsilon. That's why it is uniformly convergent. Okay, now you see in the so now let us analyze the function sequence function. Okay, it is given to be nx plus sine of nx square divided by n, which is x plus sine nx square divided by n. Correct? Now this is the function given to you. Okay, so here you can notice that it has sine function in it. And do you guys familiar with any inequality involving the sine function? So so sine function or trigonometric functions, trigonometric sine and cosine functions are bounded by 1. Okay, so we know that sine theta modulus of that is bounded by 1 for theta in R. Okay, this is what we know. So this is what we are going to use. That's the this is what we want to use uh, in order to bound that difference by some epsilon. So how do we do that? So for that, if I consider this difference, okay, if I consider this difference inequality, it is basically x. It is basically x sine x square divided by n minus x, because x f is the identity function. So x gets cancelled out by this, and we are left with sine of nx square divided by n. Okay, now let's take the modulus of both sides. So we will get modulus of this. Now we know that sine nx square, okay, sine theta is smaller than or equal to 1. So we use that uh, and we divide this whole expression, this whole inequality by 1 over n. So we will get that this quantity is smaller than 1 over n. Okay, so this quantity is smaller than 1 over n. And this, everything whatever I have written is true for all x in the closed interval 0 comma 1. Okay, so this, so what we have gotten, we have gotten an inequality involving the difference of sequence function with the limit function and 1 over n. Now the only part is remaining is to associate epsilon to this inequality. Okay, now how do we associate that epsilon to this inequality? That is what we are going to see. Any question at this point? Okay, so now we start with uh, epsilon. So take epsilon to be a positive real number. Okay, now for given this epsilon, one can always find out a natural number. Okay, n in n such that 1 over n will be smaller than this epsilon. Okay, 1 over n will be smaller than this epsilon. So this is in particular the Archimedean principle, Archimedean property. Okay, so what does this say? This says that if you have two real numbers, so I take 1 and epsilon, so you can find out a natural number n such that 1 such that n epsilon will be larger than 1. You need to take both to be positive. So both real numbers to be positive. So I've taken two positive real numbers, 1 and epsilon. Okay, and I can find out a natural number n such that 1 is larger than n epsilon. Okay, so this is called Archimedean principle, Archimedean property. Okay, so now from this property we will get, for the same n, we will get that 1 over n is smaller than epsilon. Okay, that's what we are using over here. Now once you have this, once you find out such natural number n, so this inequality will also hold for any n, any natural number n which is larger than n. So 1 over n will be smaller than 1 over capital N. And since 1 over capital N is smaller than epsilon, so we will get that 1 over n is smaller than epsilon. Okay, for all n greater than or equal to, you take. Okay, so we will use, now we have gotten this inequality. So for a given epsilon, I can choose an n such that, okay, or in particular there exists an n such that this 1 over n is smaller than epsilon for all small n larger than the capital N. Okay, now we use last two inequalities. The first inequality, which is this, which gives us the bound between the absolute value of the sequence function and the limit function by 1 over n, and the second inequality, which is that 1 over n is smaller than epsilon. Okay, now from these two inequalities, what can I say? I can say that for epsilon greater than 0, there exists a natural number n such that fn minus fnx minus fx, which was sine of nx square divided by n, which is smaller than 1 over n, okay, is smaller than epsilon for all n bigger than or equal to n, and for all x in the compact domain. So for any epsilon greater than 0, there exists an n such that this inequality is true. Okay, so this implies that fn converges to f uniformly. Okay, in particular, this question is true. This statement is true. Any question in this question in this problem? Any question on this problem? Okay, so let's move on to discuss the next question. So in question number 2, we have a statement given, and again it's a true and false type question. So let's first read out the question. Let f and g are two functions from R to R, and consider the sequence fn and gn of functions such that fn converges to f and gn converges to g uniformly. Then fn times gn converges to fg uniformly on R. So this question is like, if we have given two uniformly convergent sequences, then their product is also uniformly converged. Okay, this question is asking whether this statement is true or not. So clearly this statement will false, because uniformity uh, uniformity of two functions, product of uniform converging two functions, will not give you a uniformly convergent sequence of functions. Okay, so we will see an example how we can construct such an example. So so first we need to start with two uniformly convergent sequences. Okay, Fn and Gn. So let's take these two sequences. So first define your Fn to be x. Okay, which means that for for all n in natural number. Okay, so in other words, for given any n, you have a identity function. So it is a constant sequence of functions. Okay, so it is a constant sequence of functions. That is your Fn. And now we take the Gn. Let's take Gn as well. Just a second. Okay, so yeah, so now define Gn. So we define Gn to be 1 over n. Okay, so this function is for each n. So if I fix n, then this gives me a function which is constant. Okay, for each n, it is a constant function. But if you vary n, then this is a sequence 1 over n. Okay, which converges to 0. So now, so we have two things to see. So if I consider their product, point-wise product, okay. Uh, so if I consider their point-wise product and define the product function, which will be then it will be x over n. Okay, it will be a x over n type function. It is x over n, and now we have a few things to prove. The first thing is that Fn converges to f uniformly. Similarly, second also that Gn converges to G uniformly. Okay, and third point we need to show is that Fn times Gn does not converge to Fg uniformly. Okay, so these are the three claims we need to prove. Okay, so first claim is that Fn converges to F uniformly. So let's see that part. Okay, so let me first write down the uh, statement we are trying to prove, that Fn converges to F uniformly. That's the first part we are proving. Okay, so first of all, we need to find out what is F. And how do we find out F? So we find out F by its pointwise convergence. Okay, we see where does this function sequence of functions converges if I just fix a point in my domain. Okay, so we first perform the point wise convergence. Okay, so for that, fix x in R. So after fixing point in R, we get a sequence of real numbers. Correct? We get a sequence of real number in R. Now we further know what is this sequence of real number because we know the definition of Fn. So Fn is given to be x only. Okay, so it will be a constant sequence. It is a constant sequence x. Okay, because my x is fixed. So it is a constant sequence. Is a constant sequence, and we know the limit of the constant sequence. So this constant sequence will converge to, so clearly fn x will converge to x. In particular, okay, so fn x will converge to x. Now this fn x, okay, because I have chosen my x to be arbitrary, it is not it is fixed, but it is arbitrary. I can this convergence doesn't depend on x. So so in particular, what I can say that fn x, sorry, the sequence fn converges to identity function pointwise. Okay, so we can say that the sequence of function fn converges to identity function pointwise. Okay, now once we know that, once we know the converging function to which the function sequence of function converge, now it's time to check for the uniform convergence. So we now check the uniform convergence. Okay, so how do we do that? So we need to find, so let's take epsilon greater than 0. Okay, we need to find out, sorry, so let's take epsilon greater than 0. Now we need to find out a natural number n such that fn minus identity, which is what, which is nothing but x minus x will be smaller than epsilon. Okay, but notice here that x minus x will be 0, and I have taken epsilon to be greater than 0. So this inequality, okay, this whole inequality will be true for any n, for any natural number n. In particular, I can take uh, n to be 1, okay, the first natural number. Uh, so I can say that there exists a natural number n such that this happens to be true for all n greater than equal to 1 and x in R. Okay, so this is the proof. So in other words, Fn converges to F uniformly. Okay, is this fine? Is this proof fine to all of you guys? Any question? Okay, if there is no question, we can move ahead and prove the second part of this problem. So in the second part, we have claimed that Gn converges to G uniformly, converges to its pointwise limit uniformly. So first, again, we repeat the similar steps. So first step is we need to find out its pointwise convergence. We need to find out its pointwise limit. Okay. So Gn is given to be 1 over n. Okay, Gn is 1 over n. So Gn is 1 over n. Now let's take 1 over n. Okay. So yeah, so first fix x in R. Okay, because I'm talking about the pointwise limit. First fix x in R. So now this sequence of g over n, gn, so this gnx becomes, it is already 1 over n. So it is already given to be, it is a constant sequence. So it is 1 over n. Yeah, so in other words, we get a sequence gnx in R, okay, and this sequence is 1 over n. for n in natural number. Okay, so this sequence is 1 over n for n in natural number. Yeah. Now, uh, yeah. Now we know. Now we only need to know that what is the limit of. Uh, now the question is the limit of this sequence 1 over n, and the answer we already know that sequence this converges to 0. So the pointwise limit of g and x is 0 function. Okay, so our g of x is 0. Okay, now we hunt for the uniform convergence to this point. Now we hunt for the uniform convergence to this point. So for that I will use the next page. Okay, so for uniform convergence, we start with epsilon, take epsilon to be greater than 0, and now we need to find out an n in natural number such that gn x minus g of x, which will be 1 over n minus 0, is smaller than epsilon. Okay, so now how do we find out such for all, and this happens to be true for all n greater than or equal to capital N. Okay, so now the question is, can we find out such n? And again, I go back to the argument given in the first question. By the help of basically this page in particular, by the help of Archimedean principle, which is written on the right hand side, I can find out a natural number n such that 1 over n is smaller than the given epsilon. Okay, so that's what I use here, and so we know that there exists n in natural number such that 1 over n is smaller than this by Archimedean property of R. Okay, by Archimedean property of R. So thus Gn minus G is smaller than n, is smaller than epsilon for all epsilon in n and for all x in R. Hence, Gn converges to G uniformly. Okay, so what we have proved? We have proved two things. First thing is that Fn converges to F uniformly, and second is Gn converges to G uniformly. Now the only thing that is remaining to show is that Fn times Gn product basically, which will be x by n. Okay, product of these two functions will be x over n. Okay, this does not converge to fg. Now what is fg? Fg is identity function times 0 function. It will give you 0 function to 0, converge to 0 function uniformly. Okay, so that's the third point uh, we are remaining to check. It is remaining to check. Okay. So why I'm not doing at this moment right now? I will do it. But this function in particular, you just look at this example. This is also an example of a sequence. Okay. So you can also treat this as an example of a sequence of function. Sequence of functions that converges to zero function pointwise, but does not converge to zero function uniformly. Okay, so this is also an example of such function, a sequence of function which converges to zero function pointwise but doesn't converge to zero function uniformly. Okay, so yeah, so this I will prove that this particular sequence of function is not uniformly converging to zero in the next question, which is exactly the statement that I have written in red just now. Okay, so any problem till this point? Uh, you can ask me questions if you have any problem, and then I will discuss the next question. Okay, so if there are no questions, so let's move on and ahead and prove this sequence of functions. Uh, Sequence of function not converging to zero function uniformly. Okay, yeah, so that's what the question number three that I was talking about. Let fn be a sequence of function such that it converges to zero for all x, basically pointwise. Uh, then the sequence converges uniformly to the zero function. So this example is not true. So this is not true, and I will give the example for the false statement. So basically, this example will work in particular to prove that it is not uniformly convergent to zero function. Okay, so yeah, so now question is, consider the sequence, consider sequence of function hn x, which is also fn type gn of x given by x divided by n. Okay, for x in R. Okay, now we consider this sequence Hn, and we need to first check that. So claim number one is that Hn x converges to zero function. Okay, Hn x converges to zero function pointwise. Okay, that's the first claim. Claim number two, that Hn x does not converge to does not converge uniformly. Does not converges uniformly. Okay, so first we will prove the claim number one, and we will move on to prove that claim number two. So pointwise case. So pointwise convergence, we have so fix x in R. Okay, so we get, after fixing x in R, we get a sequence hn x, which is equal to, let's take this point to be x naught. So hn x naught by n in R. Okay, we get a sequence in R. Yeah. Now, limit. So in other words, we need to find out limit of x naught over n is what? Okay, so clearly this limit will be zero. But how to prove that? For that, you need to start with x naught minus n, and the claim is that it is zero. So how do we prove that limit converges to something? So we start with, for epsilon greater than zero, again we need to find out some n in natural number such that this absolute difference, which is equal to x naught by n, is smaller than epsilon. Okay, okay. So again we use the Archimedean property, and we apply Archimedean property on these two numbers. So clearly x naught and epsilon are two positive, are so both are positive real numbers, because I'm taking the modulus of x naught. So these are two positive real numbers. So there exists a natural number n such that such that x naught can be measured by epsilon some n times of epsilon. Okay, so yeah, so in particular I will get x naught by n uh, being smaller than epsilon. Okay, and now this will be true for all. This will also be true if I take larger n. Okay, larger n than larger small n's. Okay, then capital N. So yeah, so this is true, and this, whatever I've written in between, is called the Archimedean property of R, okay, and because of this property I have found out an n. So this will hold true for all n greater than equal to n. Okay. So this is the pointwise convergence. So it is pointwise converging to 0 function. Now let's check for the uniform convergence. Okay. So the claim is that it is false. It will not be converging to 0 function uniformly. So what we need to prove, what we need to do is to find a sequence. So find a sequence xk, okay, k for k in natural numbers. We need to find a sequence of natural numbers in R such that fn such that uh, for some epsilon greater than 0, g sorry h n of xk minus h of xk, this is larger than epsilon for all n greater than some capital N. Yeah, basically for all n in particular. So for all n. Okay. So in particular, we need to find out a sequence of points where this absolute difference will not be smaller than epsilon. Okay. So for that we need to understand the nature of the sequence. So sequence HNX is x by n. Okay. So if in some sense if I consider a points like n square type or n cube type points. Okay. So let me take uh, xk to be k square. Okay. Or for simplicity, let's consider the same notation. So let's take xn to be n square. So whenever this n and this subscript n, both subscripts n's are going to match, it will give me n. Okay, so what do I mean is that, okay, let's take k square. So whenever this k will be equal to n, okay, so the value of this will be n square divided by n, which is n, and this n and this n will be larger than the epsilon. Okay, because I'm choosing epsilon to be small enough so that it is smaller than all the natural numbers. Okay, so first of all I choose my epsilon to be smaller than 1. Okay, and then consider the sequence xk to be k square, correct, for k in natural numbers. That's what we consider. Now the difference of these two will be larger than epsilon. So now if I consider the difference, because h is 0 function, so the only difference which it will be n, and this will be larger than epsilon. So it is in particular contradicting the um, uniform convergence argument. Okay, so this sequence is not uniformly convergent. Is this fine with all of you? So in particular, this question indeed gives you this particular example gives you a counter example for this question as well, for this question number 3 as well, and it also gives you a counter example for the second question as well. So it gives you counter example for two question uh, in one go. So this is important. So this is a kind of like a useful uh, counter example, useful sequence of functions to consider to start with, okay, to understand, because it is giving you two counter examples. Okay, so if there are no questions, we can move ahead uh, with the next question. Okay, so question number 4. It is again a statement given to you, and you need to say whether it is true or false. And what is the question? Let us just quickly have a look at it. So let f be a real value function of real variable, and consider the sequences fn and gn of functions from R to R such that gn converges to zero function uniformly on R, and the absolute difference between fn and x is bounded by gnx for all x in R and for all natural numbers. Now the claim is that fn converges to f uniformly. Okay, so this statement is true, and how do we prove that? The idea is to use this inequality given. So we already know that gn is uniformly convergent, okay, and we can see that there is a absolute difference between fn and f, which is bounded by gnx, okay, and gnx converges uniformly to zero function. So uh, so for so we will use the uh, for given epsilon, we will get some natural number n, which gives the uniform convergence of gn. We use the same n, and then for those n, I apply this inequality, because this inequality is true for all n. So for a restrictive natural number, this will also happens to be true. So I apply this, and I will get this difference will bounded by epsilon. Okay, and this natural number n doesn't depend um, on the point you have taken. Okay, because it is coming from the uniform convergence of gn. Okay, is this fine? So I will give you a couple of minutes to solve this question, and then I will give you the solution. Okay, because this is not an hard question to solve. So yeah, and then we will. So after some time, I will give you the proper solution to this question. Okay, so let me give you the solution to this problem. So as I've explained it to you that we will use the uniform convergence of Gn to get the uniform convergence of Fn. Okay, and the same natural number will work. So the independency of that natural number will be will remain. So yeah, so we have two things in our hand that gnx. Sorry, we have two things in our hand that fnx minus fx. This is bounded by gnx. Okay, so and this will clearly bounded by if I take the absolute value because it will be either be equal to or it will be positive because it will be equal only because it is larger than some positive value, so it has to be positive, it can't be negative, so it needs to be same. Okay, so if I either consider the absolute value of gn or not, it doesn't matter. And this inequality is given to be true for all x in R and for all n in natural number. Okay, so this is the first inequality given. The second inequality I will get from the uniform convergence of gn. So it is given that gn converges to zero uniformly. Okay, so that means for epsilon greater than zero, there exists a capital N uh, in natural numbers such that gnx is smaller than epsilon for all n larger than or equal to capital N. Okay, yeah. So let me start with some epsilon. Okay, so take epsilon to be positive. Now I need to find out the natural number n. So uh, for this epsilon, I will have the uniform convergence. Okay, for this epsilon, there exists n in natural number such that gnx, this modulus is smaller than epsilon for all n greater than or equal to this, correct? And for all x in R. Okay, so we have this bound, correct? So now I use this similar n. Okay, so choose n in natural numbers. Then for n greater than or equal to this, we consider the inequality which is fn x minus fx modulus smaller than gnx. Okay, and now this absolute value is smaller than epsilon. Okay, so this implies that for epsilon greater than 0, there exists a natural number n such that this fnx minus fx, this is smaller than epsilon for all n greater than or equal to n and for all x in R. Okay, so in other words, fn converges to f uniformly. This completes the proof. Okay. Okay. Any questions? Okay, if not, then let's move on to discuss the next question. So in question number 5, we have to find out the limit of this integral. Okay. Uh, so again, it is given to be statements, true statement. So let us directly jump into this uh, question. So we need to find out the limit n tends to infinity of this integral. Okay. So how do we find out that? So it is first thing to notice that this the integrand is basically given in terms of n and x. Okay, there are two variables. So you can treat this integrand as a sequence of functions because it has a natural number appearing in it. Um, so that's what I do. So first I consider a sequence of function fn x to be this. Okay, and you only need to consider and this sequence of function on a restricted domain. You don't need to consider on whole of r. You only need to look at the limits of this integral. It is from 1 to 2, so only consider integrand from 1 to 2. Okay, from 1 to 2. So we have considered a sequence of functions defined this way such that for x varying in the closed interval 1 to 2. Okay, so now we want to calculate the limit of this integral. Okay, uh, so how do we do that? So whenever you have a limit of some integral to find out, it will be better if I can take this limit inside and then calculate function the limiting function of this sequence of convergence. Okay, and I integral that convergent function. That will be better. But when can I switch limit? When can I take limit inside the integral? Okay, we can only take limit inside the integral when it is uniformly convergent. So we use this fact uh, that if fn converges to f uniformly, then integral of the limit of the integrals, okay, some a to b of fn dx is equal to the limit of f, which is nothing but the limit of fn. Okay, so we use this fact to prove that. So first, for that, we need to show that this fn converges to f uniformly, and first we need to find out what is that f. Okay, so again, uh, number one, point-wise convergence. So we look for the point-wise convergence. So for that, let's say fix x in R. So after fixing x in R, we get a sequence of fn x equal to e to the power minus x square. Or let's take this point to be x naught. It will be easier for the clear distinction. So then I get a sequence, okay, and it is a sequence of real numbers in R. Now, what is the limit of this? So limit n tends to infinity of this sequence. So it clearly goes to, because I assume that you guys are familiar with the graph of the exponential. So exponential on the when it tends to the negative side, it tends towards to 0. Okay, so it goes to 0. Okay, so the limit of this function is 0. So in particular, you can, um, yeah, in particular, you can consider this function, which is function, you consider this function hx, which is the exponential function, some constant, which is a square, which is x naught here, x naught times x. Okay, so this function e to the power minus x, if it is a continuous function, and uh, okay, it is a continuous function. So as you go to, as x goes to infinity, this function goes to 0, and you are considering its limit. So so as n tends to infinity, it will be equal to 0. So that's what we are using. So it is a continuous function. So we use the continuity of this function to prove that the limit is 0. So I leave this intermediate step for you to figure out. I've already given the hint to you. Okay, so once we know that this is the pointwise limit, okay, sorry, the limit of the sequence is 0. So in other words, the pointwise limit of this sequence of function is 0, and since x naught is arbitrarily chosen, uh, since our x naught is arbitrarily chosen, so we get is that fn converges to 0 pointwise. Okay, fn converges to 0 pointwise. That's what we get. Okay, so yeah, so we know what is f now. What we know that what is the converging function where the sequence converges. We know that function now. So now the second part is to prove that it is convergent, uniformly convergent. So for that, uh, we actually use the continuity part. Okay, so for that, we use the bounded convergence theorem. Uh, yeah. So first notice that we need to find out this absolute difference to be smaller than some epsilon. Okay, for some n greater than equal to capital N. For all n greater than equal to capital N. Now, what is this difference? This difference is nothing but e to the power minus n x square. Okay, and x we are taking in this closed interval 1 comma 2. So this is a continuous function. Okay, this is a continuous function, and it can go up to some maximum value. Okay, so in this closed interval, it is continuous function. If I fix n, let's say, so it is a continuous function on a closed interval. So it there must be bounds. So you can find out the bounds on it, and let's say it is bounded by, for let's say e to the minus 2x square, it will be going to the reverse side. So it is bounded by 1. We can take 1 as the bound, correct? One can take 1 as the bound. So it is bounded by 1. It is always bounded by 1. Okay, in this domain, it is bounded by 1. So this is fine with us, because whatever value you take, you will be towards the right hand side. So this will be equal to or smaller than 1. It cannot go beyond 1. Okay, No, it cannot be even equal to 1. It always has to be smaller than 1. So in particular, what I'm saying is that if you look at the graph of this function, so it is like this, and it hits 1 when it is 0. And when I'm considering the domain, if I look at minus x square domain, so it is basically this part, minus 1 and minus 4. So I'm looking into this domain, and my n is also going to be larger, n is also positive, so these two things are positive, so it will always be in the negative side. So wherever it is, it will always be smaller than 1. So 1 is the bound to this difference. Okay, so yeah, now we use this fact which says that uh, if fnx and fx is bound by some n, okay, then fn converges to f uniformly. Okay, and this result is known as bounded convergence theorem. Okay, this result is known as bounded convergence theorem. So I use this theorem to say that this to say that fn converges to f uniformly. Okay, and now once it converges to f uniformly, we know what to do. We know, oh, I'm out of paper. Okay, so once it is convergent to f uniformly, we can come back to the original problem, and now we can apply this result, okay, which says that if it is uniformly convergent, I can take the limit inside. That's what I do. So this integral then will be equal to 1 to 2 of f dx. Now what is f? F was 0, so it is 1 to 2 of a 0 function, which will be 0. So hence this statement is true. The limit of this uh, function is 0. Limit of this integral is 0. Okay, so any question on this? I will wait for a couple of minutes and then we will move on to discuss the next question. Okay, so since there are no question, let's go move ahead to discuss the next question number 6. Okay, so in this question, uh, f is given to be uniformly continuous function on R. Okay, and fn is a sequence of functions defined in this way. Okay, f taking values on x plus 1 over n. Now we need to show that fn converges uniformly on R to this function f. Okay, so let's prove this question. So first, here are two things. F is given to be uniformly continuous, and then uh, fn is defined in terms of f. And the third thing is that f converges. We need to prove that f converges uniformly on R to f. So, so we will first start with recalling what is f being uniformly continuous. Okay, what do we mean by that? So we say f, which is a function from real of a real value to real value, is uniformly continuous on R if for given epsilon there exists a delta which is only dependent on epsilon. Okay, such that fx minus fy is smaller than epsilon whenever the distance between y and x is also smaller than delta. Okay, that's what the definition is. So this is what given to us, and now we define f and x to be f of x plus 1 over n. Okay, so and this is true. This is defined for all x in R. Okay, so first of all, if I fix x, then we get a sequence which is fn x, fn x naught, which is equal to f of x naught plus 1 over n. Okay, so we get this sequence. And now if I find out the limit of this sequence, it will be f of x naught because f is continuous function. Okay, so what do we just recall the continuity? Continuity means if you are approaching to a point x naught, this 1 over x naught plus 1 over 1 over n is a are points in R which are approaching to x naught. Okay, if you are approaching to x naught, then the limit of that limit of the corresponding limit of the function on that sequence will be equal to the limiting value will be equal to the function evaluated at the limiting value. Okay, that's what it is. That's what it is. This is what the continuity. So point wise, clearly, we can say that clearly f and x converges to f point wise. Okay. Now we need to check for the uniform convergence. Okay. So we need to check for that f and x converges to fx uniformly. Okay, so for that we start with take epsilon to be greater than 0. Okay, now consider the difference between these two functions. So this is difference is nothing but fx plus x, fx plus n 1 over n minus fx, correct? This difference, I'm looking into this difference. So I want this difference to be smaller than epsilon, but this will happens to be true whenever x plus 1 over n minus x, the distance between these 2 points, will be smaller than delta. Okay, so what is this delta? So if I understand this distance difference, so it is 1 over n distance difference. Okay, and now I can uh, for given epsilon, one can find a natural number n such that 1 over n will be smaller than epsilon. Okay, one can find such n. So we take so now take your delta to be this, take your delta to be epsilon only. Okay, so and now we apply the uniform continuity of f on R. Okay, so we start with epsilon, which is given to us. We have a delta which is again equal to epsilon, and now this fn plus x minus fx, which is actually the difference between the fnx minus fx. So this difference is smaller than epsilon because difference is smaller than epsilon because the distance between xn is 1 over n, which is smaller than delta, which is equal to epsilon. Okay, so this implies that fnx converges to f. Okay, so in particular I have found out, so this n, so there exists an n in natural number. So this fnx converges to f uniformly. Okay, so this completes the solution of this problem. Any questions? I will wait for a couple of minutes. If you guys have any doubt, you can ask me. Okay, so if there are no questions, so we can move ahead and discuss the next question. Okay, question number 7. Uh, so in this question, I have given a sequence of functions, uh, and it is given to be 1 over 1 plus x and denominator to the power whole to the power n, and this x is varying in the closed interval 0 comma 1. Now we need to find the pointwise limit of f of the sequence fn on this closed interval 0 comma 1. Now, does this fn converges uniformly to f on the closed interval 0 comma 1? That's what the question is. So first we need to find out the pointwise limit of the sequence. Okay, that's the first part. Now in the second part is we need to see whether this fn converges uniformly to f on this closed interval 0 comma 1. Okay, so I will give a few minutes for you guys to uh, try solving this question. Okay, and then I will discuss the solution of this problem. Okay, I hope it is fine with you, because I think the first part you can try giving your shot first, and then I will discuss the solutions. Okay, so let's let's take a couple of minutes, and then I will discuss the solutions. Okay, so since I've given you a few minutes to think about this question, and now it's my turn to discuss the solution. Okay, so uh, first we need to find out the pointwise limit of this sequence of functions. So, and the procedure is again same. We fix a point and then we try to see where does this converge. Okay, so first is pointwise convergence. Okay, so fnx is given to be 1 over 1 plus x to the power n. First fix some x naught in R. We get a sequence in real number. Okay. So since my domain is 0 to 1 only, so let's stick to that part. So yeah, so we know that 1 plus x naught, 1 plus x naught to the power n. If I consider this sequence, so this will go to infinity as n tends to infinity. Okay, so this will goes to infinity as n tends to infinity. Why? Because simply the reason is for given any natural number m, given any natural number m, you can find uh, you can find a large enough n, okay, such that 1 plus x naught to the power n is larger than this m. Okay, so for example, you can take m itself. Okay, you can take m itself. So now why this m will be larger than this? Because 1 plus x naught is larger than 1. Okay, 1 plus x naught is larger than 1 because x naught is a positive number. So this is larger than 1. If I, yeah, 1 plus m is larger than 1. And if I take m, okay, which is, if I take m, uh, yeah, so it is larger than 1. So whatever the power I will take of it, so if I take its m power, okay, so this will lie between 1 and 2. So if I take its m power, it will be larger than the m itself. Okay, so one can also see by the binomial expansion as well. If you expand it, um, you will be able to see the coefficients coming, and so on. So this is going to be true, and this will be equal to. So for example, if I take uh, m to be equal to 1, this is already true. Okay, so if I assume it for, let's say if I assume it for k, so I'm proving it by induction, this fact. So I'm proving this by induction. So if it for m equal to 1, it is already true. Now if we assume for k, so 1, sorry, k smaller than 1 to the power x naught plus k, and now we need to prove for k plus 1. Okay, so now k plus 1 is smaller than this. Okay, and now this right hand side is clearly smaller than 1 plus x naught to the power, if I just multiply it with instead of adding. So basically a plus b is smaller than ab, where a and b both are larger than 1. Okay, so yeah, so by induction it is true. So yes, so we get this, and now since 1 plus x naught to the power n tending to infinity as n tends to infinity, 1 over 1 plus x naught to the power n will tend to 0 as n tends to infinity. For all x naught in this close open interval 0 and close 1. Now if I take, so you can carefully notice here that I have only taken a point. Okay, sorry, I have taken a point which is not equal to 0. Okay, so what happens when it is equal to 0? It when it is equal to 0, then x naught is equal to 0. This sequence of fn x naught, which is fn 0, becomes 1 over 1 plus 0 to the power n, which is 1, becomes a constant sequence. So this constant sequence will converge to 1 only as n tends to infinity. Okay, so in other words, this fn of x converges to f, where fx is 0, sorry, it is equal to 1. Mm, yeah, when x is equal to 0 and x elsewhere. Okay, so this is what, uh, and this is pointwise. So we have proved this for pointwise. So pointwise it is converging to this. Sorry, it is not 0. It is sorry, it is not x. It is 0 actually. Yeah. So for pointwise, we have proved that it is that your uh, sequence of function is converging to a discrete value function. Okay, it is discrete because it is on the half of the interval it is taking on whole of the interval it is taking almost all points, it is taking value to be 0, and except at x equal to 0 it is taking value 1. Okay, so it is so this sequence of function is converging to a discrete value function. Okay, now we come back to the second part. So in the second part, it is asked that does this function converges uniformly? So the answer to that is no, it doesn't converge to the uniformly, because because note notice notice that um, for each n, fn x is a function which is defined in this way. Fn x is, yeah, on 0 comma 1 interval. Okay, for each, if I fix n, this function fn x is a continuous function. Okay, because it is basically division of two continuous function, and the denominator is a polynomial which is a continuous function, so it is a continuous function in particular. Okay, so fn x for each n, it is a continuous function. So this sequence is a sequence of continuous functions. It is a sequence of continuous functions. It is a sequence of continuous functions. Okay. And now we use another fact which says that if Fn converges to F unif- uh, uniformly, and each Fn is a continuous function, then their limit is also a continuous function. Okay, so their limit is also a continuous function. Okay, so now, so I will use the idea is to use the contrapositive of this statement. What is that? If each of the function is continuous, if the sequence, if I'm considered a sequence of continuous function, uh, then its limit will be continuous. So if the limiting function is not continuous, then you can have two contradictions. Either your each of your function is not continuous, or if it is continuous, then this limit is not uniform. Okay, so since f is not a continuous function, and each fn is a continuous function, each fn is a continuous function, we get that the pointwise limit is not uniform. Okay, this limit is not uniform limit. Hence, fn converges to f, but not uniformly. Okay, so uh, this completes this question as well. Okay, so this statement, so this is no, and this function is 0 and 1. It takes 0 when it belongs to this interval, and when x equal to 0 it is 1. Okay, so yeah, so this is yeah, so this completes this solution of this question number 7. Okay, and this is the last question of the discussion. uh, so I hope you have understood this all of these questions, uh, and if you have any final doubt in any of the question, then please ask now. I will wait for a couple of minutes. And if you are watching on YouTube, then you can write down your doubts in the comments. I will try to answer them um, whenever it's possible. Okay. Okay, so let's end this discussion session here. Um, okay, so